let us take a recap of BEC, what we have learned so far. We will talk about this pressure and number equations. But very importantly, what we have seen is that if there are a large number of particles which are bosons, and these bosons have no occupancy restriction, that how many bosons can occupy a given quantum state. In that case, under certain conditions, it is shown that the excited state occupancy is restricted, or it is bounded by some value. So, if the number of particles or number of bosons in the system are much larger than that, then the rest of the particles will occupy the zero energy state or the ground state of the system. And this number can be extremely large because the ground state has really infinite occupancy, which is what we have shown. And based on that, now this state is called as the Bose-Einstein condensate. This we have gotten from two equations, which are the pressure and the number equations. Now, we will recall them just once and then go on to discuss critical temperature. That is the temperature below which such a condensate occurs, or and above that, this is an ideal Bose gas with no condensation property, which means that at larger temperature T greater than Tc, there is occupancy, all these bosons can occupy all the available energy states, and there is no condensation. The third thing that we will do is that we will discuss in brief Bose-Einstein integrals and talk about the Riemann zeta functions, which are very important in this case, because there is a particular Riemann zeta function which we have seen, which puts a restriction on the number of particles and so on. And the pressure expression also involves another Riemann zeta function and so on. We will talk about the order of phase transition. Now, this is a very important discussion. It is important to decipher what would be the order of phase transition, because we are clear that there is a phase transition occurring from a gas of free bosons in occupying all quantum states of the system, and below a certain temperature the number of all the ground state is macroscopically occupied. So, this is the transition that is occurring, and we need to know about the phase transition or the order of the phase transition, and similar phase transitions we will do later in a different context. We will talk about this the temperature dependence of fugacity and the chemical potential, and we will derive expressions for pressure and internal energy of a Bose gas. And finally, we will talk about the specific heat, which would eventually comprehensively answer this order of the phase transition, or rather it will sort of create some kind of confusion that this specific heat would be shown to be continuous across a transition, and it is only the derivative of the specific heat is discontinuous. Okay, so, that would eventually have to be settled, that what is really the order, because a normal definition, or rather the traditional definition of phase transition, is which order of free energy becomes discontinuous, and that decides the order of phase transition. Let us look at the velocity distribution of the Bose gas. This we have seen before. This is Tc greater than T, or rather, so T greater than Tc, I am so sorry, T greater than Tc, and this is T equal to Tc, and this is T less than Tc. So, you see that there is a peak that is developing at the center of this plot, and this is actually the Vx and Vy, the velocity plots, and it is it is shown as Vz. So, we can write it as Vz as here. So, this can be written as Vz. Anyway, so what it means is that it is a density of particles in the Vx equal to 0 and Vz equal to 0 are increasing, okay, and the dimensions of these systems are shown. So, that tells you that the particles are cooling down. So, the velocities are going to 0, and you have this density decreasing, which now these particles actually correspond to k equal to 0 state, because Vx and Vz, or Vx and whatever, if you call it Vx and Vy, then these are the velocities. So, largest number of particles correspond to this velocity equal to 0, and hence they must be corresponding to k equal to 0, and that is the 0 energy state that we talked about, that is macroscopic accumulation of particles. Okay. We will come back to this, and so let me remind you of these pressure and number equations. So, the pressure of an ideal Bose system is written as 1 over lambda cube, and this G 5 by 2 ZF. Once again, lambda is equal to h over root over 2 pi mkt, and this G 5 by 2 are called as a Bose-Einstein integral. ZF is equal to exponential beta mu, and this is a pressure expression. We have shown that epsilon equal to 0 contribution to the pressure is negligible. In fact, we will show that when all this ground state of the system is macroscopically occupied, the 0 energy state does not exert any pressure. So, around T equal to Tc, there will be some smaller number of particles in the excited states, and the entire pressure of the Bose gas would be due to those particles and nothing that reside in the 0 energy state. Okay. So, and we also have n minus n 0 over V, which we call as n E x c over V. This is equal to 1 over lambda cube and a G 3 by 2 ZF. Okay. So, these are like these two important equations of our for our consideration. The pressure goes as this G 5 by 2 ZF and 1 by lambda cube, and this is 1 by lambda cube G 3 by 2 ZF. And we know that this chemical potential of the Bose gas that approaches 0 from the negative side, because the chemical potential of a Bose gas needs to be negative, because otherwise the occupancy would be undefined or it will not have any meaning. So, now in the limiting case, mu approaches 0 from below, which means that ZF, the limiting value of ZF for our system is equal to 1, or it is in the limit it tends to 1. So, that is the limit that we are talking about, and ZF to be anything other than 1, or when we have the classical limit, then ZF is not close to 1 and ZF is very small. Okay. So, it is much smaller than 1. So, this is what we have done, and from there we have shown that these G 3 by 2 ZF at ZF equal to 1, this quantity is like 1 plus 1 by 2 to the power 3 by 2 plus all that. This has a closed expression which is called as a Riemann zeta function, and this has a value 2.612. Okay. So, this is very interesting to note that if you write this down in terms of this 2.612, so n excited by the volume, that is the number of particles in the excited state divided by the volume, is equal to some xi 3 by 2 or zeta 3 by 2 as a Riemann zeta function divided by lambda cube. So, this is like 2.612 divided by the de Broglie volume. So, the quantum statistics becomes important when these particles are enclosed in a de Broglie volume. Okay. This is what is the quantum limit and so on, and of course, we sort of know that your ZF is actually obtained from this relation, that is n 0 divided by n 0 plus 1, and this is nothing but equal to 1 in the quantum limit, or in the, let us call it a BEC limit. Okay. And this is what we have been saying, and that is why we have put ZF equal to 1 in this formula, and we got a closed form for this expression. Okay. Now, it is important to get the transition temperature. This is, that is below which temperature or below what temperature, what does it depend upon, such that the condensate forms, that is all these particles, they macroscopically occupy the ground state of the system. So, that is the transition temperature of the system. So, above which there is no BEC, below which there is BEC. So, and this is very easily obtained from this expression that your total number of particles, this n is total, n0 is that corresponding to the ground state, n-exc is the number of particles that can occupy all the excited states put together. Okay. So, this is the convention that people follow, and then we are following that as well. So, n has to be now greater than this quantity which is like v t to the power 3 by 2 and then 2 pi m k whole to the power 3 by 2 divided by h cube and this xi 3 by 2. Okay. So, this is the critical condition, or not the critical, but the n has to be larger than that for BEC to occur, and in that case only the excited states will have restricted occupancy. So, any number that is greater than that would eventually come to the ground state, whose occupation is infinite for all practical purposes. Okay. So, if you convert this inequality into an equality, so we will convert this into an equality sign and then calculate the Tc equal to h square by 2 pi m k, and we have n divided by v and then z 3 by 2 and okay. So, this is the expression for Tc. What it depends upon? It depends upon, of course, the mass of the particle, and so mass of the bosons that we are talking about. N by v is nothing but called as the density of particles, and of course, other fundamental constants such as h and k and so on. So, it depends upon, as I said, that these two quantities, and if you really do this, calculate this, this will give you some number, which is if you put say for example helium 4, and why we are taking this example of helium 4, that is because for long it was considered that helium 4 undergoes a Bose-Einstein condensation below certain temperature called as a lambda temperature, and this was discovered around 1940, around that time. And there is a lambda point transition at 2.176 Kelvin. So, there is an experimental value, and if you actually use this formula that you see above, then if you put mass of this equal to the mass of the helium atoms is equal to 6.65 10 to the power minus 24 grams, and the specific volume or the inverse of density as 27.6 centimeter cube per mole, then the Tc, put this into this equation, let us call it as equation 1 for now, and then the Tc comes out to be 3.13 Kelvin, and this is not too different from 2.17 Kelvin or 18 Kelvin, and so for long this was considered to be a BEC or experimental determination of BEC. As I said, this was in 1940, around that time, but however actual BEC was discovered much later. So, this is not really BEC, but it was understood very quickly by Landau that this is called as a superfluid state. So, below this temperature, this lambda point temperature, which is 2.17 Kelvin, the bosons or the helium atoms, they lose viscosity completely, and when they lose viscosity, they there is a free flow of these atoms, and it sort of turns out that they do not comprise of, or rather the interaction between the bosons of the helium atoms cannot be neglected, and hence it cannot be termed as BEC, because BEC we have been talking about that it is really in the ideal Bose gas. So, so it was kind of not taken as an example of BEC, but definitely superfluidity happens here in this helium gas. And the superfluid behavior is what we talked about, that they lose viscosity completely and become a superfluid. Okay. Alright, so we get this transition temperature and so on. So, there is a nice picture that emerges, and we will show this picture here, and this picture tells you that you see there are two lines that you see, and where there is a XC and let us call it as TC as we have been calling, and then we call it a XC, and this is a ZF. There is just slightly different notations being used here. And so, what you get is that you get this below T equal to Tc. If you look at this plot carefully, below T equal to Tc, that is all the way from 0 to 1, you see that the blue line is rising and the red line is falling, and the red line is the BEC, that is the condensate, and this is actually the excited state occupancy. Okay. So, basically between T and T equal to 0 and T equal to Tc, that is between T by Tc equal to 1, and this is often termed as reduced temperature small t. So, this is often used in the phase transition terminology, that you write it like a small t, which is a dimensionless parameter. So, that is why there is the x axis has no dimension, neither y axis has, because this is just a number of particles. Okay. Just a number, and it is a number as well in the x axis. So, between 0 and 1, this consists of a two fluid system, where there is a condensate density, which is given by this N0, which decreases as temperature increases. Okay. And at some point, they cross each other, which means that the condensate fraction and the excited state occupancies are equal, and then as T becomes close to Tc, this thing goes to 0, the red curve goes to 0, which means the condensate fraction goes to 0, and these excited state occupancy goes equal to N. Okay. So, that is the total number. So, if you add the values of red curve and blue curve at any point, they will give you capital N, which means the total number of particles. Okay. So, there are so you can understand it that there are these there is a ground state, or which contains N0, and the line on top, that is including all the excited states, which contains NEX number of particles. Okay. So, at any temperature, it is a combination, or it is a superposition of these two fractions, and one of the fractions go to 0 at T equal to Tc, the condensate fraction, and the excited state occupancy go to 1 at T equal to Tc, and then of course, the condensate fraction, the red line continues to be 0 and the blue line continues to be 1. So, here we have a gaseous phase, which is the blue line, gaseous phase. Why we are calling it as a gaseous phase as opposed to the condensate phase. So, that contains Ne, let us call it NEXC, or you can call it just Ne also. Okay. This is equal to N into T by Tc whole to the power 3 by 2, and also it consists of a condensed phase, or a condensate, let us call it a condensate, having a N0, which is equal to N into 1 minus T by Tc whole to the power 3 by 2. Okay. It is important to get this exponent 3 by 2, because this exponent can be easily seen from this lambda cube dependence, which we have shown here, rather here. You see that there is a lambda cube dependence, lambda goes as T to the power half. So, 1 by lambda cube goes as T to the power 3 by 2, and that is where the 3 by 2 fraction comes in. And so, this is a sort of a phenomenological model to understand that what is happening below T equal to Tc, and above T equal to Tc is very clear. All of them are allowed to occupy the excited states. There is no need for them for a macroscopic accumulation at the ground state, at this lowest energy state, and all this N excited becomes equal to N. And the experimental verification that you see for the condensate fraction, the left hand side is a theoretical thing which we just shown here. The red line is the same as this line, and you see that there is this experimental curve in for a 3-dimensional harmonic trap. The particles show this kind of a fall off of the condensate fraction, and at t equal to T c it kind of goes to 0 and then remains 0 thereafter. Okay. All right. So, let me now spend a little bit of time, it is a bit of digression, but it is an important digression because we need to understand this Bose-Einstein integral, because a lot of these quantities that we discuss, which means that we discuss about the fugacity of the gas, we discuss about the chemical potential, we discuss about pressure, internal energy, specific heat, etc., that all depends upon these dependence of these ZF or mu on temperature, because these mu tends to 0 as you know as the Bose BEC occurs, but how it tends to 0 is an important thing, because we need to understand the scenario just below the transition, that is T just less than T c, we can call it as T equal to T c minus, and just above T c, which we can call as T equal to T c plus. Okay. So, this is an important thing, and we have to understand the Bose-Einstein integral. So, let me quickly show you the Bose-Einstein integral. We have defined it, and let me show you the limiting cases and so on. So, we can just write it as G n z. We know Z is equal to ZF, but we without writing it explicitly as ZF for this particular case, we can simply write it as Z, with Z is some quantity, some parameter. This is defined as x to the power n minus 1, and there is a sum over L equal to okay. So, this is really will do that in just a while, but x to the power n minus 1 Z inverse exponential x minus 1 dx. So, this is the integral actually. Now, for small z, what we can do is or rather you can not specifically for small z, but you can do an expansion of this denominator for all values of, if you keep all powers of z, then it can be written as G n z. This is equal to 1 by gamma n. Gamma n is a gamma function. So, this is 0 to infinity x to the power n minus 1 sum over L equal to 1 to infinity z e to the power minus x whole to the power L dx. Okay. So, we have this thing as we can just do a bit of simplification for us to be able to cast it in a form that is more familiar. So, it is x to the power minus n, and we have a z to the power L here. So, we have a z to the power L x to the power n minus 1 e to the power minus L x, because this integral is over x. So, z can be taken as constant, and this is dx. Okay. So, this term is like z e to the power minus x plus z e to the power minus 2x and so on. Okay. So, this we write it like this, and if you make a bit of substitution, that is L x equal to some x prime, then we can write this as sum over L equal to there is a sum over L equal to 1 to infinity, which I forgot here. Okay. So, this and then we have a z to the power L gamma to the power n, and because of this transformation we have 1 by L to the power n minus 1 and x prime to the power n minus 1 exponential minus x prime, and we have a dx prime by L. Okay. This is just simple by this substitution of L x is written as some other variable, which is x prime. Okay. So, I will come to this in just a while, and let me sort of write it here, and then we will come back to this, and this is equal to okay, we can write it here as well. Okay. So, this is equal to L equal to 1 to infinity and z to the power L, L to the power n, and this is zeta function, zeta of n, and where we have used that the gamma function is defined as 0 to infinity and x to the power n minus 1, e to the power minus x, e to the power minus x dx. And so, this is on a general footing, that this is a definition of the Bose-Einstein integral, and we know that we have z is same as the fugacity zf, and zf takes a value, the BEC limit, it takes a value equal to 1, and these are the things that are of importance. I mean, these xi of these 3 by 2, which is what we get, this is equal to this value, which is 2.61238. In fact, just the first 3 digits are used, which we have seen. So, this Riemann zeta function is plotted as a function of this z, or what we call as n here. So, it is plotted as a function of n, and at n equal to 1, that is at zf equal to, okay. So, this is actually the Riemann zeta function, which is z, okay. And this at z equal to 1, in fact, the way we have defined it, let us keep it as n, which is 3 by 2, but this is knowing that this is at zf equal to 1. So, this is the kind of curve that you get for xi 3 by 2, and so this is important because we would be interested in various temperature dependencies which are important. Okay. So, now let us see that how ZF depends on temperature. And so, what we have is that instead of temperature, what you can say is that let us see the variation of ZF, with V over lambda cube. Okay. Now, this V is called as a specific volume, where small v equal to capital V by n. Okay. So, it is known that lambda varies as t to the power minus half. So, V over lambda cube, that varies as t to the power 3 half. So, now the temperature dependence of the fugacity will come through this V by lambda cube. So, we are interested in the region where we have this 0 less than t less than T c. So, we are interested in this region, and in this region you have 0 less than, so V by lambda cube, 0 is less than equal to V by lambda cube is less than equal to that 2.612, that number which is that zeta function, and remember this your n is equal to V t to the power 3 by 2 divided by h cube and 2 pi m k whole to the power 3 by 2, and these 3 by 2 and so on and so forth. Okay. And of course, we have ZF to be equal to 1, and why it is equal to 1? Because this is really equal to 1 minus 1 over n 0, and n 0 being very large, the second term goes to 0. And so, this clearly of course gives you that lambda cube by V. I just invert this. Remember, this equation is the defining equation for Tc. So, this is the same equation for Tc. So, if you put this critical value of this n, or rather this n has to be larger than that, but if you put a equality sign, then you get a Tc. So, lambda cube by V, it is this maximum value of which is equal to 1 or rather it is 2.612. So, whenever you have V over lambda cube to be much greater than 1, then G 3 by 2 ZF will be much smaller than 1. So, ZF will be, so this is greater than 1 of course, ZF will be much smaller than 1, and this is the classical limit. We are not interested in this limit, but we should know that in the limiting case what happens. So, we have in this Jn ZF expression, we have this expansion is valid, this expansion of this is valid in the classical case if we are in the limit where ZF is very small, and will be enough to keep a few terms. So, of the order of ZF. Okay. So, ZF versus temperature, the plot really looks like this. Okay. For all the way from T equal to Tc, so this is T and this is ZF, and all the way up to Tc it looks like this, and then of course, it falls off like this. Okay. And this is ZF equal to 1, and this is equal to ZF equal to V by lambda cube, or lambda cube by V rather. Okay. So, in this lower than Tc, we have the ZF nearly remaining constant at a value 1, but as you go to temperature larger than Tc, then ZF starts falling, and this is when the occupancy of the high energy, or rather the excited states, they increase, and they can now accommodate a large number of particles, and then of course, that leads to the destruction of the condensate. Okay. So, this is the ZF expression, and I will probably do it on a separate platform, that how the this chemical potential looks like. The chemical potential really looks like this, and so mu versus temperature. So, this is the value 0. So, at T equal to 0, mu is equal to 0 in the limiting case, and then as temperature increases, the mu becomes negative. Okay. All right. So, these are the definitions, or rather these parameters, how they behave with temperature, because we need to understand the condensate properties just below Tc and just above Tc, or if you want to see the critical properties of the condensate, that is how it behaves as T tends to Tc, either from above or below. Mainly we are interested in how it behaves from as T tends to Tc from below, that is from 0 side. And there are now enough evidences that this or rather you understand this condensate much better, that is a very large number of particles will start occupying the ground state at low temperature when the fugacity becomes almost equal to 1 and mu becomes almost equal to 0. Then there will be a sort of macroscopic accumulation of particles in the lowest energy state, which is called as a Bose-Einstein condensation. Okay. Let us now look at the pressure of the Bose gas. Okay. This is not too difficult, because we already know the expression for pressure, which is equal to kT over lambda cube. We have written that earlier, and this Bose-Einstein integral, this is that index n, if you remember, and this is that ZF. Okay. Okay. And this has a form, closed form, which is the Riemann zeta function. Okay. So, this is really equal to the kT over lambda cube and xi zeta, sorry, not xi, zeta this. Okay. Now, that tells you that lambda is since lambda is proportional to t to the power minus half, the pressure of these condensate fraction, this goes as t to the power 5 by 2, right, because there is a t on top and then lambda cube goes as t to the power 3 by 2, 1 by lambda cube, then this goes as t to the power 5 by 2. So, this tells you that this is independent of the volume. And because it is independent of the volume, and then we can write down this the compressibility as 1 over V with a minus sign and a del V del P T. Okay. P is not a function of V. So, this will like a state with infinite compressibility. So, what it means physically is that you can pack any number of particles into the system, because we also know that the ground state occupancy is infinite. And because the pressure is independent of the volume, which is very different than the classical ideal gas that we have seen, this is an important result which tells you that the compressibility is infinite and you can pack or you can load any number of particles in the ground state. Okay. Let us just try to calculate what is the pressure at T equal to Tc or T less than Tc. It hardly makes a difference. So, T equal to Tc or even T less than Tc, because it is constant. So, P at Tc, T equal to Tc, okay, is nothing but I will just have to substitute the expression for Tc, which we have obtained earlier, and this is a kTc whole to the power 5 by 2 and this zeta function at this 5 by 2. So, if you substitute Tc equal to h square by 2 pi m k and this n divided by v 3 by 2 whole to the power 2 by 3. So, this you substitute here in this, and then you get a P at T equal to Tc is equal to this nice ratio of these two zeta functions, zeta 5 by 2, zeta 3 by 2, and we get this n by v kTc. Okay. This is nothing but the classical pressure or pressure of a classical gas, and this ratio, if you calculate it, comes out as because xi of 5 by 2 is equal to 1.341. Let me write down a few zeta functions which some of them are actually useful. This 1 is equal to infinity, and this 3 by 2 is equal to, very familiar to us, 2.612. Then this is 2 is equal to some value which is pi square over 6. 5 by 2 is equal to 1.341, which is what we have written. Let me write down one more. This is 3 is equal to 2 more, it is 1.202, and finally, we have another one which is equal to pi 4 by 90, and you will see that this, the last one, would be useful when we talk about the black body radiation. Okay. This it comes in the Stefan-Boltzmann law, the intensity of this, the radiation intensity. Okay. So, we already need it here, we already need this one here, and we finally would need this here. So, the zeta function is very important, and you have to understand the zeta function comes over and over again, because you are interested in solving the Bose-Einstein integral, because this would give you the expressions for pressure, etc. So, these two things, that is 1.341 divided by 2.612 gives you a nice number which is very close to 0.5, is 0.5134, and then N by V KTC. Okay. So, if you remember that your G 3 by 2 ZF, if you do not put ZF equal to 1, if you put ZF equal to 1, that is zeta 3 by 2, but this is equal to lambda cube by V, we have seen that, and this is nothing but N by V H cube divided by 2 pi m KT, that is the lambda cube term, whole to the power 3 by 2. Okay. So, one very important result is this one. Let me just draw it with a, or rather box it here, and you see that the pressure at T equal to Tc is half of the classical pressure. And where is it coming from? It is coming all from the excited state particles, the particles that are there in the excited state. So, at T less than Tc, there are particles in the excited state which you have seen from this plot, right. So, you have particles here which correspond to the excited state occupancy at T less than Tc. So, these are the ones which exert all the pressure. So, even if half of NKT by V, that comes from all these blue, the particles that reside in the excited states, and the particles that reside in the ground state exert no pressure. And this while calculating this P expression, we have actually separated out the pressure due to the ground state particle, and have shown that has no almost this can be put to 0 in the limit of infinite volume, or in the thermodynamic limit. Okay. So, all these expression that you get, or rather all the pressure that you get at T equal to Tc or T below Tc is entirely due to the excited state occupancy, and it is only half of what we have as a classical pressure, which is say 76 centimeter of mercury or 760 millimeter of mercury, and so on. This particular thing will be in stark contrast with fermionic system, because in fermionic system you will see that at T equal to 0, because of the exclusion principle, that is a hardcore condition, that there is no two fermions can occupy the same energy state, there is enormous pressure. Okay. And this pressure we are going to calculate, but that pressure is extremely large, and because of this no occupation constraints on the bosonic system, the pressure is very low. Okay. So, this is really that 0.5134 times the pressure that that you get for the classical case, or the pressure that due to an ideal gas with no, of course, no it is a classical pressure. So, no occupancy constraint, no indistinguishability, they are all distinguishable, and so on. Okay. So, this is an important point that one may want to make. And what happens to for T greater than Tc? That is, we are not talking about much greater than Tc, but just say T in the vicinity of Tc, but on the larger side, that is T greater than Tc side. So, P becomes equal to NKT over V G 5 by 2 ZF and G 3 by 2 ZF. And I am not going to put ZF equal to 1, because ZF starts deviating from these values. I mean, if Z is not equal to 1, then it has a temperature dependence, which is what we have shown here. Okay. So, at T greater than Tc, your this side of the plot tells you that how ZF falls off, but the expression will still remain that it is G 5 by 2 ZF and G divided by G 3 by 2 ZF. So, what happens for T large? So, now say we want to recover the classical limit, then you can easily show that G 3 by 2 ZF almost equal to G 5 by 2 ZF, either of them becomes equal to ZF. because that is the expansion. It is a ZF divided by ZF square by some denominator plus ZF cube by some denominator and so on and so forth. But if the temperature is large enough, then it is sufficient to keep only the first power of ZF. So, if you put it there in that expression, you get this NKT by V, which is the classical pressure. So, we get this PV equal to NKT, the ideal gas equation that we have been seeing right from the beginning. So, this is the classical gas equation. All right. So, this is quite interesting that as you recovered the classical limit, which you should, because we have said that the Bose distribution actually becomes same as the Maxwell-Boltzmann distribution at large temperature. So, this is the story with pressure, and what is the story with internal energy? This is an important thing that will show that the pressure and internal energy which we write by U, they carry the same information, because P just differs from U in this case as well as in the relativistic case by just a factor. In this case, the factor is 2 by 3 U by V, pressure equal to, and in the relativistic case it is P equal to 1/3 U by V. Okay. So, this U is can be written as, which is the basically the average energy. Okay. So, that is the internal energy, because we are talking about a non interacting Bose gas. So, this is the log of Zg. We have seen that a number of times. It is a minus del beta of the grand ln Z g, which is the grand canonical partition function. We can convert this into a del t and del t del beta, etc., and that a little bit of simplification gives this, and a del t of PV over KT at ZF and V. Your lambda of course goes as 1 by root over of T. So, this one I mean do not get this feeling. This is that PV over KT is the Bose gas expression, which is there in terms of this 1 over this expression that we have started with when we started describing the Bose gas. So, it is not the P is not just a constant. So, P depends on temperature and so on and so forth. So, this is that Bose gas expression. Okay. And so, this is equal to a KT square. It will be clear in the next line itself. This is V and a G 5 by 2 ZF and a del T of 1 over lambda cube, and this is at the ZF and well, let me write it with a square bracket here, ZF and V. Okay. So, this is simple, and now we just need to calculate this thing. So, it is a 3 by 2 KT, just del T of T to the power 3 half. So, that 3 by 2 comes here, and we have a V by lambda cube, and then we have a G 5 by 2 ZF. Okay. Now, you see that this expression is very similar to the pressure expression excepting a factor. So, if you compare the expression for pressure and the internal energy, it simply comes as U by V. Okay. So, that tells you that pressure and internal energy carry no different information. In fact, if you really plot P or U, in fact P by KTC and all that U by so P over NKTC and U over, or rather 2 U over 3 NKTC. If you plot that, then you get a like this, and that will tell you that this is as a function of T over TC, and you get a transition and this is like a T over TC equal to 1. So, that is the transition line, and this is the classical expression, which is P v by k T equal to constant. So, this classical and this is the BEC. Okay. So, beyond BEC, of course, they start I should not like write it like this, rather I should draw it like this and then carrying on there. So, this is the BEC. Let me just superimpose a red line such that it is clear. So, this is the BEC, and then of course, they become same. Okay. So, that is the expression for the internal energy, and the pressure you have already known. You already know the how the number of particles behave, and this is more or less the discussion of the Bose-Einstein condensate. So, let me just give you a brief idea about this order of phase transitions. So, this old theory of phase transition says that if you order of free energy which becomes discontinuous gives you that order of phase transition. That means, the free energy is always continuous. If the first derivative of free energy becomes discontinuous, which is like the entropy etc., then you have a first order phase transition. If the second derivative of free energy becomes continuous, then you have a second order phase transition, and so on. So, the second derivative of free energy is nothing but this specific heat. The specific heat is discontinuous, then it is a second order phase transition. Now, here in BEC, the CV is continuous, or the specific heat is continuous. I am just calling it as CV is continuous, but dCV dt is discontinuous. So, that tells in that old language that this is like a third order phase transition, but actually a more modern theory of phase transition tells you that if you can define an order parameter for a phase transition, then that is called as a second order phase transition, and we have been able to identify an order parameter. So, what is an order parameter? Order parameter is a quantity which indicates a phase transition, that is either say it goes to 0 or it diverges at T equal to that Tc. Suppose water melts. Okay. So, one can take that and water melts, and I mean melts means water becomes vapor, sorry, it is not water melts, or the solid melts, we can say. A solid melts to a liquid can be taken as a phase transition. Then you can see that the distance between the ionic distance or the atomic distance, that becomes ill defined at T equal to Tc. So, it sort of is a molten solid, or if you take it as from a ferromagnet to a paramagnet, then you see that the magnetization goes to 0 across a phase transition. So, these are called order parameters. Okay. So, we have actually defined an order parameter in this particular case, and which is the this condensate fraction, because that condensate fraction goes to 0 as T tends to Tc. So, this in principle should be a second order phase transitions, and not going by that old definition of phase transition, that which order of the free energy becomes discontinuous. So, we will carry on with this notion that if we can define an order parameter for a phase transition, that is a second order. If we cannot, then it is a first order. There is also another definition which says that this first order phase transitions that involves latent heat, and second orders do not involve latent heat. So, first order phase transitions we can write involves latent heat. Second order phase transition do not involve latent heat. Okay. And we can define an order parameter then it is a second order and where it is not possible to define then it is a first order. So, we sort of cut this long story short, and we say that since we can define an order parameter, it must be a second order phase transition, does not matter if the specific heat is continuous. So, finally, let us look at the specific heat, which is nothing but the this derivative, temperature derivative of the internal energy that we see there, and this involves a little bit of mathematics and basically the properties of this Bose-Einstein integral. I will just do it quickly, and then there will be some tutorial questions that will clarify all these issues. So, we calculate the specific heat, and so U is equal to 3 by 2 NKT G 5 by 2 ZF and G 3 by 2 ZF, and we talk about a temperature T equal to Tc plus, which means that the temperature is equal to just above the critical temperature, or you can call it Tc plus epsilon. So, this is so ZF will just deviate slightly from 1, this is what I want to say. So, Cv by Nk just divided by that. So, this is equal to 1 over Nk and del U del T Nv, this is equal to a 3 by 2, we have to take this, so it is a G 5 by 2 ZF and G 3 by 2 ZF plus a 3 by 2 T del T of G 5 by 2 ZF. Now, these temperature dependencies come, as I was telling you earlier, that these are important to know that what these dependencies are for ZF and all that, and now you have to take a derivative with respect to temperature. The first term is due to taking a derivative which is linear in T. Now, use a formula which can be derived in the tutorial. So, this is equal to the derivative of these Bose-Einstein integral is nothing but 1 by ZF G n minus 1 ZF. Okay. So, if you use this, then this second term can be easily evaluated, and this is equal to G 5 by 2 ZF and G 3 by 2 ZF, and this is equal to G 3 by 2 ZF del T of G 5 by 2 ZF. I am just doing the U by V form minus G 5 by 2 ZF divided by into del T of G 3 by 2 ZF, and this whole divided by G 3 by 2 square ZF. Okay. Without breaking the the chain of discussion, there is some algebra of course needed, and you use this formula that you see here. It can be shown that C divided by Nk has this nice form, which is equal to 15 by 4 G 5 by 2 ZF and G 3 by 2 ZF minus 9 by 4 G 3 by 2 ZF divided by G half ZF. Okay. So, the classical limit can easily be obtained. At least let us see the classical limit, and then we will see how it looks like as a function of temperature. So, in classical limit, your G n ZF is same as ZF, and for ZF equal to much smaller than 1, that is away from the quantum limit. So, Cv over Nk is that famous relation that you are aware of. It is 15 by 4 minus 9 by 4, which is equal to 3 by 2. Okay. So, that is a 3 by 2 R of these particles which only have one quadratic degree of freedom, that is the kinetic energy. Okay. So, they are not interacting. All right, and let me show you this the dependency here. So, here we have shown a pressure. So, the pressure variation is what we have shown, and you see that the right hand side is a normal phase and the left of this is a BEC phase, and these are like the transition line occurs here. So, the pressure is a constant for T less than Tc, which is what we have said, and the pressure starts decreasing as a function of the specific volume. The normal phase or the gaseous phase. So, the normal and the gaseous would mean the same thing. So, this gaseous phase is shown at two different temperatures, T1 and T2, and your T2 is greater than T1. So, T2 is this thing. So, T2 is greater than T1, and you have this V1C and this V2C, which are these critical specific volumes, which are related to this again this temperature. Okay. And this is the plot that you have for the specific heat C over Nk. Now, you see that it sort of for the condensate side. So, this is the condensate and so it rises like this and then it sort of falls like this and then becomes a constant at T large T much greater than Tc, which is this value 3 over 2. So, you see that you can still have the specific heat has a kink like structure, and this is similar to the lambda. It looks like the this letter lambda, and that is why it is called as a close to, I mean it is called as a lambda point transition and so on. So, this is the behavior of the specific heat across the transition. You see that there is a kink, and the kink is indicative of the fact that it one is that it does not involve latent heat, which means that if you are just below the transition and just after the transition, then you have some heat. So, this is a second order phase transition, and of course, the derivative of the specific heat is discontinuous because of the kink there. We can also calculate this amount of discontinuity, and that will tell us that that CV, in spite of being continuous, we still have to term it as a second order phase transition. However, dC V dt is discontinuous because of the kink structure, and this is the classical limit, and this is just here it is a gaseous phase. Okay. So, most of the discussion on Bose-Einstein condensation is done. Okay. We have gotten the thermodynamic quantities, pressure, internal energy, etc. We know that below a certain temperature there is a macroscopic accumulation in the ground state, which is called as the Bose-Einstein condensate. A little bit of algebra is needed in order to understand this, but this is unavoidable because of these complex forms of the Bose-Einstein integral. You see there is something in the denominator which is like this exponential beta epsilon minus mu minus 1 and all that, and then there is the behavior of these ZF, say for example, which we have or you can see the pressure expression. See, till Tc there is a constant pressure, and then it starts falling off. That falling off just beyond T equal to Tc has to be understood. So, that is why all these expansions of the Bose-Einstein these integrals, they are becoming important. We have shown most of them. If there is something needed, we will cover that up as well, and any thing that involves algebra will be pushed to the tutorials and or the assignment problems. Okay. We will stop here now. Thank you.